So how do we actually do this, right? Let's go back to some of the basics. Security properties can be expressed as some logical combination of safety properties and liveness properties. And those of you who have a computer science degree know what this means. Safety means something bad will not happen. Liveness means something good will happen eventually. Now, to prove this one is hard. In general, it's not doable because it's reducible to a halting problem, and that's a whole other conversation. The first one's actually doable, okay? It's doable in finite time. So let's take that for a second. Some of the examples of security properties that are safety properties. Memory safety, race conditions, escalation of privileges can all be expressed as safety properties. So how do we express them, right? So I assert there's a set of security properties that related to programs can be automatically expressed as safety properties. Or maybe some combination of safety and liveness that the liveness properties can actually be proved. And there's a set you have to manually specify them because those are probably business logics. What we need to focus on is intersection that's a set that's automatically verifiable. I don't know how big that set is. Okay, I'm just making an assumption that that's something like that. You know, maybe it's a union of those two sets. I don't know. It's a research problem. So this is what we need to be focusing on. So take security out of developers' hands. Instead of taking the source code, run it through compilation, code generation to the target code, let's think about this. Let's take the source code, run it through some kind of scanning that automatically specify a set of security properties that are relevant to this code, okay? As far as this automatic engine can tell. And let's then feed into it a set of manual specified security properties, probably done in design stage, and a set of common safety properties that may be global to everybody, that things at low level like memory safety you want to enforce. Let's take all three of them together and run through a compilation plus property checking kind of framework, okay, in compile time. And let's run through a code generator that enforces these properties, and you generate secure target code. And developers don't have to do anything. They just have to feed the source code in, okay? Maybe deal with some of the compilation results. Compilation should not be changed much. Developers can do whatever they want. That's what I want. For production code, now we were talking, the compilation piece was talking about in development, right? For code that's already in production, what are we going to do? Now, let's say this one is a code that has code injection vulnerability in it. We've got incoming exploits, and typically it will result in a code injection. Instead of let it go to the website, let's run it through a set of engines that does a few things. Signature, if you have attack signature, by all means, you should look for it. Attack signature, and some kind of very efficient automatic theorem prover tells me that with this input, oops, we're going to run into insecure state, okay? And when that happens, does dynamic instrumentation of the code, and now, voila, you've got secure web application for this particular exploit, generated dynamically. That's what we need. So, run through the life cycle, In the design stage today, we may have architecture review, we may have threat modeling, some of the companies are doing it, small number of them, and requirement gathering and whatnot. With this new model, we will add security property, safety property specification in the design stage. In development, in addition to static analysis, security testing, we've got automatic checking, verification of security properties in the way of theorem proving. And this is done in a secure development environment with low-level controls that developers don't manipulate. And in deployment, today we've got WAF, we've got pen testing. With this new model, we've got automatic generation, automatic vulnerability detection and generation of functionally equivalent code. Could be done in instrumentation, could be done in code generation, whatnot. And this is how we get our secure application lifecycle management. Okay? That's how we get our marbles back. Obviously, this is not easy to do. There are a number of challenges we have to face. Right? We have to leave the development environment untouched, largely untouched. Otherwise, developers won't use it. You're not going to get them to use a different IDE. Even integration of a different tool is going to be difficult. You have to leave the build environment untouched. The build environment is like I don't know, it's like crown jewel or something. Nobody wants you to touch that. And you have to have little or no impact on the existing development practices. And that's the challenges. And these properties also have to be true, right? We're talking about automatic theorem proving and code generation. It has to be done efficiently. You cannot be sitting there and waiting for code to respond. It has to be provably functionally equivalent. Nobody's going to let you touch their code if it's not functionally equivalent. And again, no change to existing development, testing, deployment strategy. Okay? So, is it really doable? Do we have a starting point? I assert yes, we do have a starting point. Some of the theoretical work that's been done in academia, this is about rich computer type theories used in model checking and also used in theorem proving. These new work has really actually put much advances in theorem proving today that automatic theorem proving actually conceivably can be done in runtime with efficient results. Some of the work done at Cornell by Robert Constable about correct by construction attack tolerance systems, and by Bickford about automatic generation of correct authentication protocols. The work has advanced to the degree that they can automatically generate a key exchange authentication protocols provably secure. Okay? This is a huge leap forward, being able to generate protocols. It's not quite full-fledged software yet, but protocols are a great starting point. These is about use formal methods to generate security. Go back to Jeff's point. It's not about looking for vulnerabilities. It's about generating security, and it's about doing what we know best rather than working with developers, relying on them to do it. We have to do it for them. So if you are a vendor in software security, you're I don't know if there's any VCs here, anybody who's looking to advance the state of art. You have to keep an eye on these technologies. Hopefully some of you will go back and be a chaperone, or not a chaperone, be a champion of these technologies and introduce them to industry in due time. And there's also some applied work being done that's quite interesting. It's a dynamic data flow analysis done by UT Austin and the Southwest Institute It's not a theorem proving per se, but it is taking the method of automatic code generation in runtime using static analysis they've done in compile time to guide dynamic analysis for code generation. I think has great potential. So with that, the thing to take away from this presentation are these points. We have to take security away from error-prone humans don't understand security. Okay? If you have developers who are security versed, who really know how to write secure code, by all means, right? Don't stop them. But majority of developers don't, and let's not try to get them to do that. Second point, let's build security into development frameworks and runtime environment that is not controlled by human. Okay? It's automatically done. And let's leverage on some of the fundamental work that's been done in computer science about construction logic, about rich type theories to do that. So with that, anybody recognize what this image is? This is an art by Bradford Paley. Really interesting what he did. He actually generates this automatically using a Java program. So he traces the program execution to generate an art piece like this. Very interesting. It's actually commissioned by, I think, the Whitney Museum of Art in New York. And it is a jungle out there when you look at the execution of the code like this. But we can conceivably find some order in this jungle. We just have to switch, shift our thinking a little bit. That's my contact information. Any questions? Take down my contact information. I'd love to hear your thoughts on this subject.